Okay, next exercise 4. So here we have been asked to describe in pictures or words the elements of D5, which is the set of symmetries of a regular pentagon. So just like what we did for an equilateral triangle, we have drawn the symmetries. You can see that the figures are not from a geometric construction point of view perfect pentagons, but for our purposes to find the symmetries, these are sufficient. So we have what we have done is we have named the vertices in a counterclockwise sense, starting from this one and naming them alphabetically A, B, C, D and E. So the first transformation you already know is R0, which is nothing, or it can be interpreted as rotation through an angle 0 degree. Since it does nothing, rotation clockwise or counterclockwise or about which point, that actually is it does not matter, because it leaves everything fixed. So in particular it leaves these vertices also in their respective position. It does not do anything. Then the next symmetry is R108. It's a rotation in the counterclockwise direction through an angle 108 degree, and the center of rotation is this point, which is the point of intersection of all the perpendicular bisectors of the sides. Since the pentagon is a regular pentagon, it can be proved using geometry that the perpendicular bisectors all pass through one point, and that point is the center of rotation. If you do that, so that means okay, but there is one more question. Why 108 though? That comes from this formula, which gives us the internal angle of a regular n-sided polygon. You can test this formula by putting some values of n, for which we already know the internal angles. For example, if you take n equal to 3, then you are considering an equilateral triangle. So you get the value 60. So we already know that the internal angles, each one of them is 60 degrees. Or if you take n equal to 4, then you are considering a square, and it turns out that the internal angles are 90 degrees, which is true. And if you take n equal to 5, then you get the internal angle of a regular pentagon, which turns out to be 108 degrees. So we are rotating the pentagon like this through an angle 108 degree in the counterclockwise direction about that center of rotation. What it does is that it shifts the vertices cyclically like this. E takes the position of A takes the position of B, and so on. Since the pentagon is regular, after this rotation it still looks the same, and that's why this rotation is a symmetry of the pentagon. Then the same thing is done, but now with twice the value of the angle, that is 216 degree. So now what happens? Another such rotation. So now in place of this you have this. A has shifted to the position of B, B has shifted to the position of C, and so on. Then through an angle 324 degree, which is 3 times 108. So now A comes from here to here, and all the other vertices also rotate accordingly. And finally we rotate through an angle 432 degree, which is 4 times 108, and we get this arrangement of the vertices. That is also a symmetry. Note that if you make one more rotation, then the vertices will come back to their original position, and that will give us R0 back, so we won't get anything new. So by making these rotations, we have got how many symmetries? 1, 2, 3, 4 and 5. Once these options are over, the next thing is we change the orientation of this cyclic arrangement by flipping the pentagon about this axis, which is the perpendicular bisector of the side AE, and it passes through the vertex C. Since the pentagon is regular, if you flip it like this, C will remain, C will not change because it lies on the axis of reflection. However, A and E will get interchanged, B and D will get interchanged. After this, what you do now with this new orientation, now you see, if you go alphabetically, then it doesn't go counterclockwise, it goes clockwise, A, B, C, D, E. So the orientation has changed. Or you can view it like this also. Instead of looking at the pentagon like this from this direction, you are now looking it from behind. Okay, if you do that, then from that point of view, this will be the orientation. So then we continue our rotation. We get this position in this new orientation. We have A here. Then you make again 108 degree counterclockwise rotation about this center of rotation. A will take the position of E, E will take the position of D, and so on. However, don't confuse yourselves with the orientation and the rotation. If you are finding it confusing, you just think of the rotation or the operation that you are performing to always be counterclockwise. It's just an observation that the orientation has changed. Once you have observed that, just forget about that. Okay, you continue your rotation. So A will come here, then in the next rotation, A will shift to the position of E. A will come here. Then in the next rotation, A comes here and becomes the bottom vertex, and finally A comes here. If we make one more rotation, then we will get this arrangement back, so we won't get anything new. So here our number of symmetries, we have reached the maximum number of symmetries. And from our experience with an equilateral triangle, we already know that instead of thinking of these operations as a flip followed by a rotation, you can think all of them as flips with respect to other axes of reflection. With respect to this one, you have achieved this arrangement. With respect to this one, you will achieve another one where A will stay the same, B and E will interchange their positions, C and D will interchange their positions. And like that, for every vertex, every other vertex, you will have one reflection or one flip. So that gives us in total how many symmetries? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 symmetries for a regular pentagon. 5 of them are rotations, that is starting from this one, 1, 2, 3, 4, 5, and 5 of them are reflections. Yeah, I have named this V because it's reflection about a vertical axis, but you can name it anything. Okay, you can in fact, if you want, you can name it according to the axis about which you are reflecting the figure, and that axis itself can be named using the vertex through which it goes. Every axis goes through a unique vertex. This is going through A, this is going through D. Note that the vertex on which the vertex which the axis has on it, that stays unchanged in that flip or in that reflection. Here B does not change, everything else changes. A and C get interchanged, D and E get interchanged. So these are all the symmetries of a regular pentagon, and the set of symmetries is D5, the dihedral group of degree Do we call it dihedral group of degree 5? I can't remember clearly. Anyway, a dihedral group with 10 elements. So let us see the next one. So this is exercise 5, and exercise 5 is going to be general. It asks us something about Dn itself, the group of symmetries of an n-sided regular polygon, where n can take any value greater than or equal to 3. So this is exercise 5, and what does it say? For n greater than or equal to 3, describe the elements of Dn. And there is a hint also. You will need to consider two cases. When n is even and when n is odd. And the solution goes like this. We can guess about the solution or about the general case from the few examples we have seen. We have so far seen how many? We have seen D4, we have seen D3, and we have seen D5. So the solution is like this. Dn consists of n rotations of the form where, excuse me, it's quite windy outside. I think a storm is brewing. I thought someone is knocking. No one should knock here because it's a place on the roof of my house. So if someone knocks here, then it can be something paranormal, maybe, who knows, at this hour. Zero, one, etc. n minus 1. Okay. So Dn consists of n rotations of the form, means this is the angle through which we will be rotating the figure, the n-sided regular polygon. And when n is odd, so that is only half of Dn. From the examples we have seen, D3 has 6 elements, D4 has 8 elements, D5 has 10 elements. So it's 2n. Dn has 2n elements, twice that number n. So n rotations give us only half of the elements. What about the other symmetries? when n is odd, we have to also say that the other symmetries are reflections, and in reflections, then the description of these reflections will depend on the parity of n, whether n is even or odd. So there this next thing comes, when n is odd, half of these reflections when n is odd, the axes of reflection are obtained by joining the vertices to the midpoints of the opposite sides. For example, if you have a triangle, then this is an axis of reflection. You can flip like this, which is obtained by joining this vertex with the midpoint of the opposite side. Or you can consider this axis, or you can consider this axis. And if it is a regular pentagon we have seen today, then also same thing, either this axis or this axis, or this one or this one. Okay. But when n is even, then half of the reflection are obtained by joining opposite vertices. Half of the axis of reflection are obtained by joining opposite vertices, and the other half is obtained by joining midpoints of opposite sides. For example, we have already seen the case of a square in the text. So it has 4 rotations because the value of n is 4. One of those rotations is through an angle 0 degree, so it does nothing, and the other 3 rotations are there. Now among the axes of reflection, two are obtained by joining opposite vertices, that is, in this case, the diagonals, and the other two are obtained by joining midpoints of the opposite sides, which are these vertices. So just like that, if you consider a regular hexagon or a regular octagon, there also the thing will continue to be true. So this is the complete description of the elements of Dn. In reflections and in rotations, the axes of reflection they depend on the parity of n, whether n is even or odd. According to that, the axes are determined. Okay, now next, exercise 6. In Dn, explain geometrically why a reflection followed by a reflection must be a rotation. So in Dn we have to explain geometrically that if we perform two reflections, we can do so, no? Because we have the operation of composition in the group Dn, which is just performing two operations one after another. Doing that is equivalent to performing a single rotation always. But why? We have to give reason for that. And this is my answer. So let's just first see the solution, and then we will try to make sense of it. A reflection of an n-sided regular polygon about an axis changes the orientation of the vertices or the orientation of the figure itself. So we can write changes its orientation. This we have already seen 2 times. In fact, 3 times if you count the example in the text also. If you flip, then the orientation changes. Rotation does not change orientation. Okay. When this is followed by another reflection, this is followed by another reflection, we get the original orientation of the polygon back, because if we see the axes of these two reflections can be different. You can say if the triangle is like this, then you can first flip the triangle about one axis and then again flip the triangle about a different axis. But when you do so, actually what you are doing, from the triangle's point of view, you are moving. You are looking at the triangle, say, from this point of view, from this side. From the triangle's point of view, you are now here. Now, once the flip is made, you have moved to that side. Irrespective of the axis of reflection, whether it is this axis or this axis or this axis, the same thing happens. Of course, the way the triangle is looking at you, that may change. I mean, you may look somewhat different after the flip, but that fact remains constant, that you are on this side, then after the flip you move on that side. And if you then again flip it about some axis, then you come back to this side. So the orientation comes back to the same, I mean, it comes back to the same orientation. In fact, have I lost the triangle from that day? I don't know. Let me just. I think I lost it somewhere. Anyway, we can see here itself. Suppose this is the axis. Then if I flip it about this axis, then I get A, C, B. Okay, so the orientation has changed. From the counterclockwise sense of this alphabetical order, we have gone to the clockwise sense. But then say I flip it again, but now with respect to a different axis, with respect to this axis, say, then I will get this. A and C are interchanged, B stays the same. Then I again get that counterclockwise orientation, A, B, C. Of course, the positions of the vertices have changed. That's what I was saying when I said that from the triangle's point of view, I may look somewhat different after the two reflections, but the orientation or the side of the triangle to which I will lie, that will again be the same as the original one. So the same thing will be true, you can imagine, in an n-sided polygon, because after all that is also a plane figure which has some axis of symmetry about which you are reflecting. So if you make two such reflections, the orientation will come back. So what then? What is the consequence of this? The consequence is this. Okay, but we have to mention that also. However, the vertices may change positions. The vertices will not change position if the two reflections are about the same axis. Yeah, if you are using the same axis to reflect the triangle, then first B and C will interchange their positions and then again they will interchange their positions, so you will get back the exact same arrangement of even the vertices, not just the orientation. But in general the vertices will change positions, but the orientation will be we will get it back. Since any two arrangements with the arrangement of the any two arrangements of the polygon with the same orientation are a rotation away. We have already seen this in case of the triangle as well as in case of the pentagon, that if the orientation is same, say I have the pentagon like this, A, B, C, D, E. I am not drawing the actual thing because we need to consider only the vertices. So this is a regular pentagon with this orientation of the vertices, counterclockwise orientation. Now instead of this arrangement, say I have this arrangement. Here also the orientation is counterclockwise, and these two arrangements are just a rotation away through an angle of 216 degree in the counterclockwise direction. So you can understand very easily that this will happen in a general n-sided polygon also. So that's why we are saying, since any two arrangements with the same orientation are a rotation away, a reflection followed by a reflection must be a rotation. So here the solution ends. Okay, then exercise 7 is a similar one. In Dn, explain geometrically why a rotation followed by a rotation must be a rotation. Now you may think that it's obvious. Well, geometrically it's obvious. You rotate it once and then you rotate it once more. So the ultimate result is a single rotation through some angle. But exactly how do you justify it? It may give you pause, and you may be forced to really think what can be said in the solution. But the solution, it's not my solution. Actually, this solution is available at the end of this text itself, and it's the author's solution, and it's really clever. And he says, a rotation followed by a rotation either fixes every point so it's the identity that R naught or fixes only the center of rotation. That is, either the rotation does nothing or it does something, the power is gone, or it does something, and that something is fixing all the fixing only the center of rotation and rotating the entire plane, everything else in the plane through some angle. Okay, so what can we say from this? However, a reflection fixes a line. So a rotation followed by a rotation cannot be a reflection, because it cannot fix a line. Either it fixes every point, say one rotation fixes every point and the other rotation fixes only the center of rotation. Keep in mind that for both the rotations, the center of rotation is the same, because that is the center of the insided regular polygon. If you know what I mean, how to find the center, we have already seen. If the number of sides of the polygon is odd, then you have to consider the perpendicular bisectors of the vertices. In general also, you can consider perpendicular bisectors of not the vertices, the sides. They will all pass through the same point, and that point is the center of rotation. For both the rotations, the center is the same. So either both of them fix all the points, in which case they together, one after another, if we apply them, then that operation also fixes all the points, or one of them fixes all the points and the other fixes only the center. Then their combination will fix only the center. And if neither of them fixes all the points, that means each one of them fixes only the center, then their combination either can what can you say? Yeah, their combination either fixes all the points, in which case actually they are inverses of each other. Say one rotation is through an angle 30 degree in the counterclockwise direction, the other is through an angle 30 degree in the clockwise direction. Then if you perform both of them, they will cancel each other. So their combination will fix all the points, or their combination will fix only the center, and they will change everything else. However, a reflection about some axis fixes that axis, that line. So two rotations performed successively, that cannot be a reflection. So it has to be a rotation, because in Dn we have only reflections and rotations. So, and we also know from closure property in Dn, I mean geometrically I am saying that if you perform two operations in Dn successively, in other words algebraically speaking, if you are composing the two operations, then you will get again an operation back in Dn. So it must be either a reflection or a rotation, but it cannot be a reflection, so it has to be a rotation. So a rotation followed by a rotation must be a rotation. And finally, another one of this type, exercise 8. In Dn, explain geometrically by a rotation and a reflection taken together. In either order, that is whether you are performing a reflection first followed by a rotation or the other way around, is a reflection, must be a reflection. We have already seen this happening in both D3 and D5. That is, once you flip and then you rotate, instead of that you can have a single flip about some axis of reflection. Now why does that happen? And the answer, the solution goes like this. A rotation and a reflection taken in any order change the orientation. A rotation does not change the orientation, it keeps the orientation of the figure. However, a reflection does change the orientation. So ultimately, any order you apply these two operations, you are going to change the orientation of the insided polygon. Since a rotation does not change change the orientation, because applying these two things in any order, you ultimately get the figure flipped, and hence the orientation has changed. But that cannot be achieved by a single rotation, because a single rotation, no matter however you do it, it's unable to change the orientation, it's unable to flip the thing. That can only be achieved through a reflection. So that's why. So a rotation and a reflection taken in any order must be a reflection. So these exercises, these three exercises are just they are trying to figure out what happens when we compose two elements in Dn, depending on whether each one of them is a reflection or a rotation. So from this we can get an idea of what we, of course in a particular case, a particular rotation and a particular reflection, what they will give us, that depends on what the individual operations are. But we can say in general what the type of the result will be, whether it will be rotation or a reflection. Then there is this interesting exercise 9. Associate the number 1 with a rotation. And the number -1 with a reflection. Describe an analogy between multiplying these two numbers and multiplying elements of Dn. And multiplying to elements of Dn. Let me put some ink. Multiplying two elements of Dn means composing two elements of Dn. I am not going to write anything elaborately, you can write it. The thing here is that you have this now. a rotation and a reflection. We are associating the number 1 with rotation and -1 with reflection. We have seen that if we perform 2 rotations successively, then the result is again a rotation, which is like multiplying 1 with itself and getting 1 back. If we perform a rotation followed by a reflection, or a reflection followed by a rotation, then the result is a reflection. So that is like multiplying 1 with -1 or -1 with 1 in any order and getting -1 as the result. And finally, if we perform 2 reflections successively, then that is equivalent to a rotation, which is like multiplying -1 with itself and getting 1. So without looking at the group Dn, you can look at the set of these 2 numbers and the operation ordinary multiplication to at least know what will happen when we multiply 2 elements in Dn. At least know the type of the result, whether you will get a rotation or a reflection. That is, you can see here, nicely determined just with the help of this ordinary real numbers and ordinary multiplication. And this fact that this can be done without ever calculating anything in Dn will later manifest itself as the idea of a homomorphism between 2 groups. Okay, so we will see that when we go deep into group theory. So I end the video here today. If you have any doubts, you can write in the comment section below, and in the next video we will do more exercises, and we will possibly try to finish this set of exercises and move on to actual group theory. So that's all for today. So I am signing off. This is me, Lucifer, from a mathematical room. Have a nice night.